Across the unfathomable darkness of the cosmos, something is missing. In every direction we point our most powerful instruments, we witness a spectacle of majestic consistency. We see the grand cosmic web, a shimmering tapestry of galaxies strung together by filaments of dark matter, a luminous foam of creation floating in the abyss, and behind it all, permeating every cubic centimetre of existence, is a faint primordial glow. It is the oldest light in the universe. This light is a whisper from the dawn of time, an echo of the Big Bang itself, cooled over 13.8 billion years to a mere whisper of radiation, just a few degrees above absolute zero. We call it the cosmic microwave background. It is a picture of the infant universe, a snapshot taken when the cosmos was just 380,000 years old. And this picture, this relic radiation, is almost miraculously uniform. The temperature variations from one patch of sky to another are minuscule, less than 1 part in 100,000. It is the smoothest, most perfect blackbody spectrum ever observed in nature. This uniformity is not just a curiosity. It is the bedrock upon which our entire understanding of the universe is built. It tells us that the universe began in an extraordinarily simple, hot, dense state, and has been expanding and cooling ever since. It is the ultimate proof of our cosmic origins, almost perfect. Almost. Because in one particular direction, in the sky of the southern hemisphere, nestled within the constellation of Eridanus, the river, there is a stain, a smudge on this otherwise pristine photograph of creation. It is a patch of sky that is anomalously, inexplicably cold. It is not a dramatic plunge in temperature, but a subtle, persistent chill. A deviation so large and so deep that, according to our best models of cosmology, it simply should not be there. This is the story of that anomaly, a feature known to astronomers as the CMB cold spot. It is a mystery that begins with a map of the entire universe and leads us to question the very foundations of reality. It is a journey into the heart of the largest and most profound emptiness we have ever discovered, the Eridanus Supervoid. A place that may be a simple cosmic curiosity, or perhaps the first tangible clue that our universe is not alone. To understand the gravity of this cosmic conundrum, we must first journey back in time, not just to the universe's infancy, but to our own. For millennia, humanity looked up at the night sky and saw a realm of permanence, an unchanging celestial sphere dotted with fixed stars and wandering planets. It was a clockwork universe, divine and predictable. This perception began to shatter in the early 20th century. Through the giant eye of the Hooker telescope on Mount Wilson, Edwin Hubble discovered that the faint smudges of light, the nebulae, were not clouds within our own Milky Way. They were entire galaxies, island universes in their own right, each containing billions of stars. And more shocking still, he found that nearly all of them were rushing away from us. The farther a galaxy was, the faster it receded. The universe was not static, it was expanding. This was a revelation that changed everything. If the cosmos is expanding now, it means that in the past it must have been smaller, denser and hotter. Running the clock backwards leads to an inescapable conclusion, a moment of infinite density, a singular point of origin, the Big Bang. The theory was magnificent, but for decades it lacked definitive proof, the smoking gun. That proof would arrive not with a bang, but with a hiss. In 1964, at Bell Labs in New Jersey, 2 radio astronomers, Arno Penzias and Robert Wilson, were struggling with a new, highly sensitive horn antenna. They were trying to map radio signals from our galaxy, but they were plagued by a persistent low-level background noise. It was a faint hum that came from every direction, at every time of day, through every season of the year. They checked their equipment, rewired their systems, and even famously climbed into the horn to clean out what they called a white dielectric material, pigeon droppings. But the hiss remained. It was an irreducible feature of the sky itself. Unbeknownst to them, just a few miles away at Princeton University, a team of physicists led by Robert Dick was building a detector specifically to search for the very thing Penzias and Wilson had stumbled upon. They were looking for the thermal afterglow of the Big Bang, the cooled remnant of the universe's primordial fire. When the two groups finally connected, the significance was immediate and profound. The hiss was not noise, it was the sound of creation, it was the cosmic microwave background radiation, the fossil light from a time when the universe was a sea of incandescent plasma. This discovery transformed cosmology from a field of speculative philosophy into a precision science. And for decades, the story of the CMB was the story of its perfection. Every measurement confirmed its stunning uniformity. It was a testament to a period in the universe's first moments known as inflation, a period of hyper-accelerated expansion that smoothed out any initial wrinkles, leaving the cosmos incredibly flat and uniform. Imagine a vast, crumpled sheet. Inflation is like grabbing the corners and stretching it with incomprehensible speed until it becomes almost perfectly flat. The tiny quantum fluctuations that existed before this stretching were themselves magnified to astronomical scales. These became the seeds of all future structure. The tiny variations in temperature we see in the CMB, those 1 in 100,000 ripples, are the imprints of those primordial quantum jitters. They are the blueprints for the galaxies and clusters we see today. Hotter spots represent slightly denser regions, where gravity would slowly begin its patient work, pulling matter together over billions of years. Colder spots represent slightly less dense regions, the areas that would eventually become the Great Voids. Our models, based on the theory of cosmic inflation, made very specific predictions about the size and distribution of these spots. They should be random, like the pattern of static on an old television screen. There should be a characteristic size for the larger spots, but nothing too extreme. The universe, on its largest scales, should be boringly consistent. Then came the age of space-based observatories. Satellites like COBE, and later, the Wilkinson Microwave Anisotropy Probe, or WMAP, were launched to map this ancient light with unprecedented clarity. They orbited far above the distorting haze of the Earth's atmosphere, staring into the deep past. In 2003, the WMAP team released its first full-sky map of the CMB. It was a stunning achievement, an oval projection of the entire celestial sphere, painted in shades of red and blue, representing tiny deviations from the average temperature. The map was a triumphant confirmation of the standard cosmological model. The distribution of spots, their sizes, their intensity, it all matched the predictions with breathtaking accuracy. But as scientists scrutinized the data, a few troubling anomalies emerged, and one in particular stood out. In the constellation of Eridanus, there was a patch of blue so large and so deep, it defied the statistical predictions. It was the cold spot. This region of the sky was about 70 microkelvin colder than the average. It sounds like an impossibly small number, but on the scale of the CMB, it was a 4-alarm fire. The area covered a staggering portion of the sky, spanning about 5 degrees, which at the distance of the CMB translates to a physical size of nearly 1 billion light-years across. 1 billion light-years. A distance so vast it is functionally unimaginable. A chasm of space that could contain 10,000 Milky Way galaxies laid end to end. According to the standard model of cosmology, the probability of such a large, cold fluctuation appearing purely by chance was minuscule. Some calculations put it at less than 1 in 50,000. Others suggested the odds were even steeper, closer to 1 in a million. It was, to put it simply, a statistical aberration of the highest order. Cosmologists are by nature a skeptical group. The first reaction was to question the data itself. Perhaps it was an instrumental error, a flaw in the WMAP satellite. Maybe it was some foreground contamination, some cloud of dust or gas within our own galaxy that was blocking the ancient light from behind it. But as the years went on, the evidence only grew stronger. The European Space Agency's Planck satellite, a mission with even greater sensitivity and resolution, mapped the CMB again in the 2000s. And there it was, unmistakable. The cold spot was real. The puzzle was no longer about the observation, it was about the explanation. What could possibly create such a colossal, cold imprint on the baby picture of our universe? The leading hypothesis, the most conventional explanation, is in some ways just as mind-bending as the mystery itself. It proposes that the coldness is not a feature from the early universe at all. It is not a primordial cold patch. Instead, it is an illusion, a trick of light and gravity created by something far closer to us in space and time. Something gargantuan and almost entirely empty. The theory posits the existence of a supervoid. To grasp this idea, we must update our mental image of the universe. It is not a uniform sprinkling of galaxies. Rather, it has a structure, a magnificent architecture known as the cosmic web. Imagine a three-dimensional spider's web, spun across the cosmos. The bright, luminous threads of this web are the filaments, long chains of galaxies and dark matter stretching for hundreds of millions of light years. Where these filaments intersect, we find the great galaxy clusters, the bustling metropolises of the universe, blazing with the light of trillions of stars. But between these filaments, in the vast spaces that separate them, are the voids. These are colossal regions of profound underdensity. They are not perfectly empty, but they contain far fewer galaxies, far less matter than the cosmic average. They are the great deserts of the cosmos, immense bubbles of near nothingness that make up the bulk of the universe's volume. The Eridanus Supervoid hypothesis suggests that between us and the CMB, in the direction of the cold spot, lies one of these cosmic deserts, but one of truly unprecedented scale. A void so large and so empty that it actively alters the light passing through it. The mechanism for this alteration is a subtle and beautiful piece of physics known as the late-time integrated Sachs-Wolf effect, or ISW effect. It is a consequence of Einstein's theory of general relativity and the strange, accelerating expansion of our universe, driven by dark energy. Let's construct an analogy to make this tangible. Imagine a photon, a single particle of light from the CMB, as a marble rolling across a perfectly flat rubber sheet representing space-time. This marble has been rolling unimpeded for over 13 billion years. Now, on its journey towards us, it encounters a vast, shallow depression in the sheet. This depression is the supervoid, a region with less mass, and therefore a shallower gravitational well than its surroundings. As the marble rolls into the depression, it picks up speed and energy. In the language of a light, it becomes slightly blue-shifted. It then travels across the bottom of the depression and must climb out the other side. In a static, non-expanding universe, the climb out would be exactly the mirror image of the descent in. The marble would lose the exact same amount of energy climbing out that it gained rolling in. It would emerge with its original energy, its original colour, completely unchanged. But our universe is not static. It is expanding, and that expansion is accelerating. While our marble of light is traversing the immense distance across the void, the universe itself is stretching. Dark energy is pushing everything apart. This means the depression, the void itself, is becoming wider and shallower. By the time the photon begins its climb out, the hill is less steep than the one it rolled down. The climb is less arduous. Consequently, it loses less energy on its way out than it gained on its way in. The net result should be a photon that is slightly more energetic, slightly bluer. It should create a hot spot, not a cold one. But this is where the ordinary ISW effect becomes the late-time ISW effect. In regions dominated by dark matter, gravity fights against expansion, causing structures to collapse and deepen gravitational wells over time. However, in a void which is dominated by dark energy's repulsive force, the gravitational potential decays. The void actively flattens out. This decay saps energy from the photons passing through. So as the photon enters the void, it gains energy falling into the gravitational well. But as it traverses the void, the well itself is decaying and flattening due to cosmic acceleration. The climb out is now effectively longer and harder than the fall in. The photon has to expend more energy to escape than it gained upon entry. It emerges from the other side with a net loss of energy. It is red-shifted. To our instruments, this light appears slightly colder than the light from surrounding regions that did not pass through such a void. The supervoid, this great cosmic emptiness, acts like a cosmic refrigerator for light. It was a brilliant and plausible theory. It used known physics, general relativity, and dark energy to explain the anomaly. All that was needed was to find the void. Astronomers turned their telescopes towards the Eridanus constellation, no longer looking at the faint microwave light from the distant past, but at the far more recent distribution of galaxies in the intervening space. They began a cosmic census, a deep sky survey to map the three-dimensional structure of the universe in that specific direction. The task was monumental. It required meticulously measuring the distances to hundreds of thousands of galaxies to see if there was indeed a great deficit of matter lying along our line of sight. In 2015, a team of astronomers using data from the Pan-STARRS telescope in Hawaii and NASA's WISE satellite announced a breakthrough. They had found it. There was a supervoid centered about 3 billion light-years away from us, right in the middle of the cold spot's location on the sky. It was one of the largest structures ever detected in the universe, spanning an incredible 1.8 billion light-years. Its center was estimated to be about 30% less dense than the cosmic average. It seemed the mystery was solved. The cold spot was the shadow of this gargantuan void. It was a triumph for the standard model of cosmology. But science is a relentless process of refinement and re-examination. As more data came in, as different teams analysed the structure of the void, the clean, simple picture began to cloud over. The void was undeniably there. It was immense. It was underdense. But was it empty enough? Detailed simulations and calculations were performed, modelling the ISW effect that a void of this specific size and density profile would produce. The results were troubling. The Eridanus Supervoid, as vast as it is, can only account for a fraction of the observed temperature drop. Most calculations suggest it can explain perhaps 20, maybe 30% of the cold spot's intensity. It creates a chill, but not the deep freeze we observe. The void is real, but it is not the complete answer. The shadow is far darker than the object casting it. And so, the greatest mystery of empty space returned, deeper and more perplexing than before. The most plausible conventional explanation had been tested, and it had been found wanting. We were forced to look beyond the standard model, to confront possibilities that are far more radical and far more unsettling for our place in the cosmos. What, then, are we left with? If a supervoid cannot fully explain the cold spot, we must re-examine every assumption we have made. One possibility is that we have been profoundly unlucky. Perhaps the cold spot is in fact two phenomena layered on top of each other. It could be the small cooling effect from the Eridanus supervoid, coincidentally aligned with a genuinely primordial cold fluctuation that is, by itself, quite large but not statistically impossible. The combination of the two effects would create the extreme coldness we see. It is a tidy explanation, but one that relies on a significant coincidence. And in cosmology, invoking coincidence is often a sign that a deeper truth is being missed. Another, more straightforward possibility is that it is simply a statistical fluke. Our understanding of the universe is based on the cosmological principle, the assumption that on large enough scales, the universe is homogeneous and isotropic. It looks the same everywhere and in every direction. This principle implies that the patch of the universe we can observe is a fair, representative sample of the whole. The cold spot challenges this. It suggests that perhaps the fluctuations in the early universe were not perfectly random. Maybe there are statistical outliers of this magnitude, and we just happen to live in a cosmos where one is visible in our sky. Imagine throwing 1 trillion dice. You would expect a random distribution of numbers, but it is not impossible that in one corner you might find 100 dice that have all landed on the number 1. It is extraordinarily unlikely but not forbidden. The cold spot might be that patch of 100 ones. If this is the case, it has no deeper meaning. It is just a cosmic roll of the dice that came up strange. It's an answer that is intellectually unsatisfying, a cosmic shrug that leaves the mystery unsolved, merely dismissed. But for many scientists, the inadequacy of the standard explanations is not a dead end. It is a signpost, pointing towards new physics, towards a conception of reality far grander than our own universe. This is where we enter the realm of the truly speculative, where the line between science fiction and theoretical physics begins to blur. One of the most tantalizing and extraordinary explanations for the cold spot is that it is a bruise. a scar on the fabric of our universe, left over from a violent encounter with another universe entirely. This idea stems from the theory of eternal inflation and the concept of the multiverse. According to this paradigm, the Big Bang that created our universe was not a unique event. Instead, the quantum field that drove the initial inflation of our cosmos is eternally active. Our universe is just one bubble that nucleated and expanded within an infinitely vast, eternally inflating metaverse. Other bubbles are constantly forming, each one a new universe, potentially with different laws of physics, different fundamental constants. We exist within an endless cosmic ocean of these bubble universes. Most of the time, these bubbles expand into their own pocket of space-time, never interacting. But what if, in the distant past, our infant universe collided with another? The models of such a collision are complex, but they suggest that the impact would be cataclysmic. It would disrupt the energy field within our bubble, pushing energy out of the collision region and creating a vast, spherical disturbance. This disturbance, this cosmic bruise, would be imprinted on the cosmic microwave background. It would appear as a large, unusually cold disc-shaped region on the sky, a region that looks remarkably like the cold spot. The implications of this are almost too profound to fully grasp. If this hypothesis is correct, then the faint chill in the constellation Eridanus is the first piece of empirical evidence for the existence of other universes. It would mean that when we look at this smudge on our map of creation, we are staring at a fossil from an event that predates the formation of the first atoms in our own cosmos. We are looking at a remnant of contact with a separate reality. The cold spot would be transformed from a cosmic anomaly into a gateway for our imagination, a window onto the multiverse. Yet this is not the only exotic explanation on the table. Other theories from the frontiers of physics propose different origins. Perhaps the cold spot is not a bruise from without, but a flaw from within. Some models of the early universe predict the formation of what are called cosmic textures. As the universe cooled from its ultra-hot initial state, it may have undergone a series of phase transitions similar to how water freezes into ice. When a material freezes, imperfections can form in its crystal structure. A cosmic texture is a hypothetical, far grander version of such an imperfection. It would be a vast, tangled knot in the fabric of space-time itself, a topological defect left over from a primordial phase transition. Such a texture, if it existed and then unwound, would also leave a characteristic imprint on the CMB, a pattern of hot and cold spots. Some models suggest that a large, unwinding texture could be responsible for the Eridanus anomaly. Finding evidence of such a texture would provide an unprecedented glimpse into the physics of the universe at energies far beyond anything we could ever hope to achieve in a particle accelerator on Earth. It would be a direct probe of the universe's very first moments. So, where does this leave us? We are faced with a profound cosmic mystery, a single feature on a map of the heavens that stubbornly refuses to fit our models. It could be the shadow of a supervoid, though not one sufficient to solve the puzzle on its own. It could be a statistical fluke, a 1 in a million chance that tells us nothing new. Or it could be the key that unlocks a new, previously unimagined chapter in physics. It might be the first evidence of a multiverse, a glimpse of realities beyond our own. It may be the remnant of a cosmic defect, a scar from the universe's birth. The path forward is clear, if not easy. We need more data. We need to map the Eridanus Supervoid with even greater precision. Upcoming astronomical surveys like the Vera C. Rubin Observatory in Chile will create the most detailed three-dimensional map of the universe ever attempted. It will catalogue billions of galaxies, charting the cosmic web with painstaking accuracy. These surveys will either find enough missing matter in the void to finally account for the cold spot, definitively confirming the ISW effect as the cause, or they will rule it out entirely. If the void is proven to be insufficient, the pressure will mount on the more exotic explanations. Future CMB experiments will search for the subtle signatures that might distinguish a multiverse collision from a cosmic texture or a simple statistical fluke. These theories, while speculative, make specific predictions about polarization patterns and other subtle features in the ancient light, clues that may one day be teased out of the cosmic static. For now, the cold spot remains an enigma. It is a stark and humbling reminder of how much we still have to learn. We have charted the cosmos, deciphered the echo of its creation, and built a model that explains its history with astonishing success. And yet, a single, persistent patch of cold sky whispers to us that the story is not complete. It represents a profound and tantalizing emptiness, not just a void in space, but a void in our knowledge. This is the nature of scientific exploration. It is a journey not into the known, but into the unknown. Every answer we find seems to unveil a dozen new, more profound questions. The Eridanus Supervoid, and the cold spot it fails to fully explain, is one of the greatest questions of our time. It is a silent, cold challenge, beckoning us to look deeper, to think bolder, and to reconsider our place in a universe that may be infinitely stranger and more wonderful than we have ever dared to imagine. The greatest discoveries often begin not with a flash of insight, but with an observation that just doesn't quite make sense. And for now, deep in the cosmic river of Eridanus lies the coldest, the largest, and the most compelling question in all the heavens. What is the most powerful word in human language? Is it love? Is it war? Is it time? Perhaps it is a word far simpler, a concept so fundamental we use it to define the very boundary of existence itself. That word is nothing. For millennia, it has been our ultimate descriptor for absence, the final answer to what lies beyond the stars between the atoms before the dawn of creation. Nothing. A perfect, silent, absolute void. But what if this is the greatest illusion we have ever accepted? What if the stark, desolate blackness you see stretching between galaxies is a carefully constructed deception? A cosmic mask hiding the most active and vital stage in the universe. We have spent our entire history as a species looking at the lights. The brilliant burning beacons of stars, the ghostly swirl of nebulae, the majestic pinwheels of distant galaxies. They are the landmarks of our cosmic map, the destinations of our imagination. They are the something that gives the universe its grandeur, and in our obsession with these celestial fires we have overlooked the arena in which they perform. We have dismissed the darkness as mere emptiness, a passive backdrop, the space between things. But the story of the universe, the real story, is not just written in the fire of suns, it is whispered in the unimaginable cold of the void. This is a journey into that cold, into a realm where temperatures plummet to fractions of a degree above the theoretical limit of absolute zero, a cold so profound it can freeze light in its tracks. Here in these seemingly barren frontiers of existence, we are discovering that our most basic assumptions about reality are wrong. We are learning that the coldest place in the universe is not empty. In fact, it is the engine room of the cosmos. To understand this, you must first recalibrate your senses. Imagine a silence so complete it is a physical pressure. Imagine a darkness so pure it feels like a substance. This is the intergalactic medium, the vast tenuous sea of gas and dust that fills the chasms between the great island universes we call galaxies. It is more than 99% of the physical volume of the cosmos, and for most of history we believed it was a tranquil wasteland, a cosmic desert where nothing ever happens. The distances are simply staggering. If our own Milky Way galaxy were a single grain of sand on a beach, its nearest major neighbour, Andromeda, would be another grain of sand almost 3 inches away. The space between them, that seemingly insignificant gap, is a gulf of 2.5 million light-years, an abyss of near-perfect vacuum, colder and emptier than anything we could ever create on Earth. For eons this was the picture we held. A universe of isolated fires separated by an eternity of sterile nothingness. This idea of a void was not just an assumption, it was a deep philosophical need. Ancient thinkers recoiled from the concept of a true vacuum. They believed nature abhorred it, that it was an impossibility. Yet as our telescopes grew more powerful, the vacuum seemed to be everywhere. The universe, it appeared, was mostly made of it. And this cold, empty vacuum became the default state of being, a cosmic zero, the absence of all things. But the universe always leaves clues for those willing to look. The first crack in this monolithic idea of nothingness came not as a shout but as a faint, persistent hum. In the 1960s, two radio astronomers pointed a massive antenna at what they thought was an empty patch of sky. They were searching for radio waves from the distant Milky Way. Instead, they found a mysterious uniform hiss. It came from every direction at all times, day or night. It was a persistent low-energy static that they could not eliminate. They cleaned their equipment, they chased away pigeons, they recalibrated every instrument, but the hiss remained. This wasn't noise from their receiver or from Earth. It was a signal from the universe itself. They had stumbled upon the oldest light in existence, the afterglow of the Big Bang. Today we call it the cosmic microwave background. It is the faint residual heat of creation, a thermal echo from a time when the entire cosmos was a blazing inferno. And it proves a revolutionary fact: the empty space between the stars is not at absolute zero. It is filled with an ancient invisible light keeping the darkest voids at a chilly but not absolute 2.7 degrees Kelvin. The vacuum, it turned out, had a temperature. It wasn't truly empty. It was filled with the memory of its own birth. This discovery was monumental, a paradigm shift in cosmology, but it was only the beginning. It was the first hint that the void was not a passive stage, but an active participant in the cosmic drama. The true revelation, however, would come from a place far stranger than the distant past. It would come from the bizarre and counterintuitive world of the infinitesimally small. To see the real nature of the void, you have to zoom in, far past the galaxies, past the stars, past the very atoms themselves, down into a realm governed by the ghostly laws of quantum mechanics. Here, at the fundamental level of reality, the word nothing loses all meaning. The classical serene vacuum of space vanishes, replaced by a roiling, effervescent, chaotic sea of energy. This is the quantum vacuum. Imagine an ocean that looks perfectly calm from a distance. But as you get closer, you see it is teeming with activity. Tiny ripples, fleeting waves, bubbles forming and bursting in an instant. The quantum vacuum is precisely like this. It is a place of perpetual seething creation and annihilation. Out of this nothingness, pairs of particles and antiparticles spontaneously erupt into existence. A particle of matter and its antimatter twin borrowing a sliver of energy from the void itself to exist for an impossibly short moment. Before the universe can notice their trespass, they collide and annihilate one another, vanishing back into the energetic foam from which they came. They are called virtual particles. They are the fleeting ghosts in the machine of reality. And they are everywhere. In every cubic centimetre of the emptiest space, you can imagine this quantum dance is happening, an infinite silent storm of particles winking in and out of being. The vacuum is not empty. It is a violent, unpredictable cauldron of potential. This underlying energy, the baseline hum of the universe, even at its coldest, is known as zero-point energy. It is the energy that remains when all other energy is gone. The energy of being itself. For decades, this was a bizarre prediction of theory, a strange mathematical quirk with seemingly little impact on our lives. But we have proven it exists. We can measure its subtle effects in our laboratories. We see how it can push tiny metal plates together, a phenomenon known as the Casimir effect. The pressure of these virtual particles, the faint push from this ghostly sea, is a real physical force. The nothingness of the void can exert pressure. It can do work. It is a physical entity with tangible properties. This fundamentally alters our perception of everything. It means there is no true stillness. There is no absolute calm. At its most basic level, the universe is restless. The coldest, darkest vacuum is a reservoir of boundless, untapped energy, a shimmering fabric of potential from which reality itself emerges. This is not science fiction. This is the bedrock of modern physics. The universe we see, the matter, the stars, the galaxies, may just be the persistent foam on the surface of this deep-hidden quantum ocean. And yet the secrets of the void do not end there. The hum of ancient light and the fizz of quantum particles are only two layers of this profound cosmic mystery. As we began to map the universe on its grandest scales, we encountered anomalies, gravitational puzzles that our theories could not explain. We saw galaxies spinning so fast they should have torn themselves apart. We saw clusters of galaxies held together by a gravitational grip far stronger than all their visible matter combined could possibly generate. Something else was there. Something massive. Something invisible. We gave it a name that reflects our own ignorance: dark matter. It is a mysterious, unseen substance that does not emit, reflect, or block light. It interacts with our universe almost exclusively through the subtle pull of its gravity. And it is not a minor component. All the stars you can see, all the gas, all the dust, all the planets, and all the life in the entire universe makes up less than 5% of the total cosmic mass. Dark matter accounts for over 25%. It is the invisible scaffolding of the cosmos, the silent gravitational architect that shapes the universe. And where does this mysterious substance reside? It doesn't clump together to form brilliant stars or glowing nebulae. It exists primarily as vast diffuse halos surrounding galaxies. It fills the immense cold dark spaces we once thought were empty. The void is not a void at all. It is the kingdom of dark matter. It is a gravitational gyroscope, a cosmic anchor, whose unseen presence dictates the motion and evolution of everything we can see. We are living inside a ghost. A colossal invisible structure whose true nature remains one of the greatest unsolved puzzles in all of science. But even this was not the final revelation. There was one more ghost hiding in the cold, one more force operating in the grand silence of intergalactic space. At the very end of the 20th century, astronomers made a discovery that would not only change our view of the void, but would also determine the ultimate fate of the universe itself. They were looking at distant supernovae, using them as cosmic lighthouses to measure the expansion of the universe. Everyone expected to see the expansion slowing down, as the mutual gravitational pull of all the galaxies put the brakes on the initial explosion of the Big Bang. What they found was the exact opposite. The expansion of the universe is not slowing down. It is accelerating. Something is actively pushing everything apart. Something is working against the pull of gravity, stretching the very fabric of space-time at an ever-increasing rate. This mysterious influence, this anti-gravitational force, is the most dominant thing in the entire cosmos. And once again, we have given it a name born of humility: dark energy. It constitutes nearly 70% of the total energy density of the universe. It is a phantom pressure inherent in the vacuum of space itself, a property of nothing that is driving the cosmos towards a cold, empty future. Think about what this means. The greatest, most powerful force shaping the destiny of our universe is not found in the heart of a star or the fury of a black hole. It is a property of the vacuum. The cold, dark, empty space that we ignored for so long is the very thing that holds the ultimate power over our cosmic fate. It is a silent, relentless pressure, a cosmic breath exhaling and pushing the galaxies further and further apart. So when you look out into the profound blackness of a clear night sky, what are you really seeing? You're not seeing an absence. You're not seeing a simple void. You're looking into the most dynamic, complex, and mysterious environment in the entire universe. An arena filled with the faint, fading echo of its own birth. A realm seething with a quantum storm of virtual particles popping in and out of existence in a dance of pure energy. You're staring into a vast, invisible cosmic web woven from a mysterious dark matter, the gravitational skeleton that gives the universe its structure. And you are feeling the subtle, inescapable push of dark energy, the intrinsic property of that same space that is accelerating the cosmos into an unknown future. The cold is not emptiness. The darkness is not absence. It is a presence, a physical entity, a force of nature. Our journey has just begun. We have only started to peel back the layers of this cosmic deception. Now we must venture into the heart of the cold itself, to places like the Boomerang Nebula, a celestial spectre colder than the background glow of the Big Bang itself. We will explore the frontiers of human engineering where, in laboratories on Earth, we create pockets of space-time billions of times colder than the deepest void. Here matter itself begins to behave in ways that defy all intuition, forming bizarre new states that act like a single giant atom. We will follow the scientists who are descending into deep underground mines, using the Earth itself as a shield in their quest to catch a single, fleeting particle of dark matter. And we will confront the profound, chilling implications of dark energy asking what it means for the ultimate fate of all things. The story of the universe is not the story of light, but of the darkness. It is the story of the cold. And by exploring these extreme frontiers, we are discovering that the engine of creation, the secrets of our past, and the blueprint for our future were never in the fire. They were hidden in the void all along. What if the deepest, most absolute silence you can imagine wasn't silent at all? What if the perfect blackness of the void, the very definition of nothing, was in fact humming with a secret energy, a ghost from the beginning of time? For millennia we looked to the heavens and saw an eternal unchanging emptiness, a divine stage upon which the dramas of planets and stars played out. The space between the worlds was just that space, a vacuum. The ancient Greeks called it the ether, a substance too pure for our world, but later minds stripped even that away, leaving behind a stark and terrifying concept, a perfect featureless abyss defined only by its profound cold and its utter lack of substance. This idea of the void became a cosmic anchor for our understanding the ultimate baseline of non-existence. Cold in this conception was simply the absence of heat, the slow decay of energy into a final, listless state. We imagined that if you could travel far enough away beyond the last glimmer of the most distant galaxy, you would eventually find a place where the universe's engine had finally run down a realm of absolute stillness. This journey to the heart of coldness brings us to a number, a destination that is not a place but a state of being absolute zero. It is zero on the Kelvin scale, equivalent to a chilling negative 273.15 degrees Celsius, or negative 459.67 Fahrenheit. This isn't just very, very cold. It is the theoretical flaw of reality itself, a fundamental limit imposed by the laws of physics. At this temperature, all classical motion ceases. It is the end of vibration, the final frozen frame in the film of reality. Imagine an atom no longer a frenetic dance of electrons around a nucleus, but a perfect sculpture. The restless energy that defines existence itself has been bled away, leaving behind only the strange ghostly hum of quantum mechanics, a whisper of motion that can never be truly silenced. To reach absolute zero is to achieve a kind of physical nirvana, an impossible state of perfect order and tranquility. Yet, it is a destination we can never truly reach. The very act of observing a system imparts energy to it, and the laws of thermodynamics themselves conspire against us, decreeing that reaching this ultimate state of cold would require an infinite amount of work. Absolute zero is a horizon we can approach getting tantalizingly infinitesimally close, but one we can never cross. It remains a theoretical paradise of stillness, a concept more than a reality. For a long time we assumed that the vast empty oceans of intergalactic space must be the closest thing to this impossible ideal. Drifting in the dark, far from the warmth of any star, an object should, over cosmic timescales, radiate away all its heat, eventually settling into a state of near-perfect cold a hair's breadth from the universe's temperature floor. This was the logical, intuitive picture of our cosmos islands of fiery energy in an endless frozen ocean of nothingness. And it was a picture that was completely and wonderfully wrong. The discovery of the universe's true nature didn't come from a grand, deliberate search for the cosmic temperature, but from an annoyance, a persistent and maddening hiss in a radio antenna. In 1964, at Bell Labs in New Jersey, two astronomers, Arno Penzias and Robert Wilson, were trying to use a large horn antenna for radio astronomy, but they couldn't get a clean signal. No matter where they pointed their instrument day or night, season after season, they were plagued by a faint uniform microwave hum. Their frustration grew with every failed attempt to eliminate the noise. They recalibrated their instruments. They checked every connection, every wire, every amplifier. They climbed into the great horn itself and scrubbed it clean, evicting a pair of pigeons that had made a nest inside, and clearing away what they delicately termed white dielectric material. But the hiss remained. It was everywhere. It came from every single direction in the sky with the same unwavering intensity. This wasn't noise from Earth, nor was it radiation from the sun or even from our own Milky Way galaxy. This was something else, something older, something that permeated the very fabric of space itself. They had, through a combination of scientific rigour and sheer accident, stumbled upon the single, greatest confirmation of our cosmic origins. They had found the afterglow of the Big Bang. What their antenna had detected was not a sound, but a light that had been travelling across the universe for 13.8 billion years, a relic from a time when the entire cosmos was a firestorm of unimaginable heat and density. We call it the cosmic microwave background, the CMB. It is in a very real sense the oldest photograph you will ever see. To understand this ancient light, you must cast your mind back to an age of utter strangeness, to the universe's infancy, a mere 380,000 years after the Big Bang itself. In this primordial era, the universe was not the dark, transparent expanse we know today. It was a completely different beast, a searing, opaque fog of plasma. The temperature was thousands of degrees so hot that atoms as we know them could not exist. Instead, protons and electrons zipped about in a disconnected frenzy, a chaotic soup of charged particles. And critically, this cosmic soup was so dense that light itself was trapped within it. A photon, a particle of light, would be born from the heat, only to travel a minuscule distance before slamming into a free electron being absorbed and re-emitted in a random direction. It was like trying to see through a star. The entire universe was a brilliant, featureless furnace screaming with energy, but utterly impenetrable to sight. Then the universe crossed a threshold. As it continued its relentless expansion, it cooled. The temperature dropped to a point where the frenetic dance of particles began to slow. Suddenly, for the first time, the negatively charged electrons could be captured by the positively charged protons, forming the first stable neutral atoms of hydrogen and helium. This moment is known as recombination, and it was a transition as fundamental as water freezing into ice. In an instant, cosmically speaking, the universe's dense glowing fog cleared. The free electrons that had acted like a billion-year traffic jam were now bound up inside atoms. The photons, which had been trapped in an endless game of pinball, were suddenly liberated. They were free to travel unimpeded across space, and so they did. In every direction from every point in the cosmos, this first light flooded the newly transparent universe. This was the birth of the cosmic microwave background. But the light that was released that day was not the faint cold microwave radiation we detect now. It was a brilliant, intense glare with a temperature of nearly 3,000 Kelvin, shining with a colour like that of a blacksmith's forge. For any observer who could have existed then, the entire sky would have glowed with a uniform brilliant yellow-orange light. But as this light began its epic journey, the universe it was travelling through was still expanding, and this expansion had a profound effect on the photons themselves. The very fabric of space-time was stretching, and as it stretched it pulled the waves of light apart. This is cosmological redshift. It's like a note played by a musician on a train that is speeding away from you. The sound waves are stretched out and the pitch drops. In the same way as the universe expanded, the wavelength of this primordial light was stretched longer and longer. Its energy dissipated. Over billions of years, the brilliant visible light of recombination was stretched down the electromagnetic spectrum from orange to red, then to infrared, and finally into the microwave portion of the spectrum. The cooling ember of creation's fire became a faint cold whisper. The 2.725 Kelvin temperature that Penzias and Wilson measured is the temperature of that whisper today. Space isn't empty, and it isn't at absolute zero because it is filled completely and uniformly with this fossilized light. Every cubic centimetre of the void, the space you might imagine as the ultimate nothingness between galaxies, contains on average over 400 of these ancient photons. They are streaming through you right now, a harmless invisible rain from the dawn of time. They are the universe's ambient chill, the baseline temperature of everything, a primordial bath that prevents anything in the cosmos from ever reaching the true silence of absolute zero. This discovery reshaped our entire understanding of the universe. It was no longer an eternal static stage, but a dynamic evolving entity with a history, a story of a fiery birth and a long, slow cooling. The CMB became the bedrock of modern cosmology, a direct window into the conditions of the early universe. It was a message in a bottle, and we were finally learning to read its contents. But as we built more sensitive instruments launching probes like COBE WMAP and Planck into space to map this ancient light with exquisite precision, we uncovered a deeper, more profound mystery. The maps they sent back were astonishing. They confirmed to an accuracy of 1 part in 100,000 that the temperature of the cosmic microwave background is the same everywhere. No matter which direction you look from the constellation of Orion to the Southern Cross, the temperature of that 13.8 billion-year-old light is 2.725 Kelvin. This uniformity is a staggering puzzle. How could regions of the universe that back at the time of recombination were so far apart that they could have never exchanged light or heat have ended up at the exact same temperature? It's like finding two people on opposite sides of the Earth who have never met or communicated yet, have their body temperatures synchronized to within 1,000th of a degree. It defies conventional explanation and points to an even earlier, more violent period of expansion in the universe's first fractions of a second, a theory known as cosmic inflation, which stretched a tiny, uniform patch of the universe into the vast cosmos we see today. This near-perfect smoothness, however, contains the most important secret of all. It is almost perfect, but not quite. Buried within that incredibly uniform temperature are minuscule variations, tiny fluctuations that are the key to our entire existence. These are temperature differences of only a few millionths of a degree, imperceptible ripples on the surface of a vast calm ocean. But these maps of the CMB with their splotches of slightly warmer red and slightly cooler blue are nothing less than the blueprints of creation. They are the genetic code of the cosmos. For every one of these infinitesimally warmer spots in the ancient sky represents a region where the primordial soup was just a tiny fraction denser than average, and every slightly cooler spot represents a region that was slightly less dense. These were the seeds. The universe in its very first moments was not perfectly smooth. It was seeded with these quantum fluctuations, microscopic variations in density, that were then magnified to astronomical scales by the explosive growth of inflation. The light of the CMB carries the snapshot of these seeds just as they were beginning to sprout. In the immense darkness that followed for hundreds of millions of years, gravity went to work on this subtle cosmic tapestry. The slightly denser regions, those warmer spots on our maps, contained just a little more mass. Their gravitational pull, though infinitesimally stronger, was relentless. Over eons, they began to pull in matter from the surrounding less dense regions. The rich began to get richer. What started as a difference of 1 part in 100,000 slowly, patiently, and inexorably grew. These were the gravitational wells, the cosmic potholes into which the first gas clouds would fall, ignite, and become the first stars. These stars would gather into the first galaxies. These galaxies would then be pulled together by the gravity of yet larger density fluctuations to form the great clusters and superclusters of galaxies that stretch across the universe today like a vast, shimmering web. Everything you see and everything you are is a direct consequence of those tiny random imperfections in the afterglow of creation. The iron in your blood, the carbon in your cells, the oxygen you breathe, all forged in stars that could only have formed because of these minuscule temperature differences. We are the descendants of a quantum flicker at the beginning of time. Our Earth, our Sun, our Milky Way galaxy, all of it is just one of the warmer, denser spots on that ancient map, a seed that has blossomed over 13.8 billion years of cosmic evolution. The profound cold of space, therefore, is not an ending. It is not the signature of a universe grinding to a halt in a featureless void. Instead, it is the canvas. The faint frozen light of the cosmic microwave background reveals a universe that was born not in perfect symmetry, but with the subtle, beautiful flaws that would allow for complexity, for structure, for life. This primordial chill is the starting point to the pregnant emptiness from which all things came. But how did it happen? How in this near-perfect, achingly cold environment did gravity manage to coax these tiny seeds into the magnificent cosmic structures we witness? The answer lies not just in the seeds themselves, but in a mysterious invisible substance that lurks in the cold darkness, a substance that would become the true architect of the cosmos. And so we had painted ourselves a portrait of the cosmos defined primarily by its overwhelming emptiness, a silence measured in light years, and a cold that approached the absolute end of all things. This was the grand stage seemingly barren between the brilliant isolated actors we called stars and galaxies. But a new kind of seeing was on the horizon, a way to listen for whispers in the vacuum we had assumed was mute. The story of this revelation does not begin with a thunderous discovery, but with a subtle nagging inconsistency, a cosmic crime scene where the evidence refused to fit the theory. For decades, astronomers mapping our own Milky Way encountered a persistent and frustrating paradox. When they measured the distances to remote star clusters, their calculations kept coming up short. The stars in these distant families appeared fainter and often strangely redder than their known properties suggested they should be. It was as if a celestial fog invisible to the naked eye was dimming the cosmic lighthouses we use to navigate our galaxy. For a time, this was dismissed as errors in measurement, the inevitable uncertainties of a young science, grappling with unimaginable scales. But the discrepancy would not disappear. It was systematic, a universal dimming that grew more pronounced the deeper into the galaxy we looked. The truth began to coalesce in the 1930s through the meticulous work of astronomers like Robert Trumpler. He realized this wasn't an error at all. It was evidence. The space between the stars was not a perfect vacuum. It was contaminated. Something was out there, a substance so diffuse and so cold that it cast no light of its own, yet it was substantial enough to absorb and scatter the light of distant suns. This was our first introduction to the interstellar medium, the ISM, the breathtakingly tenuous material that pervades the gulfs within our galaxy. To call it a medium almost feels like an exaggeration. In the densest parts of this interstellar haze, the vacuum is still more perfect than any we can create in a laboratory on Earth. Imagine a cathedral the size of a continent, and inside there is but a single grain of sand and a few molecules of air. That is the scale of density we're confronting. The dust responsible for reddening the starlight is not like the dust in your home. These are microscopic grains of silicates and carbon, tiny specks of soot, and sand forged in the death throes of ancient stars and cast out into the void. They are unbelievably sparse, yet over the immense distances between stars their cumulative effect is profound. They act like a cosmic filter, preferentially scattering the shorter, bluer wavelengths of light, allowing the longer, redder wavelengths to pass through more easily. It is the very same principle that gives us our brilliant red sunsets on Earth, but painted across a canvas thousands of light years wide. The void, it turned out, was not empty. It was merely dusty. And it wasn't just dust. Accompanying this sparse sprinkling of solid matter was an even more rarefied gas, mostly single atoms of hydrogen, and helium, the primordial building blocks of the universe itself. This gas was the true phantom of the cosmos. It was colder than the deepest ice age, hovering at temperatures just a few tens of degrees above absolute zero. At such frigid temperatures, these atoms emit virtually no visible light. They are inert, ghost-like, drifting in a darkness so complete that for all intents and purposes they might as well not have been there at all. Our eyes, the very instruments that had opened up the heavens to us, were blind to the vast majority of the matter in our own galaxy. The universe we saw, the brilliant tapestry of stars against a black velvet curtain, was a profound illusion. We were seeing only the decorative lights while completely missing the architecture of the building itself. To see this invisible architecture, we would need to invent a new kind of eye, one capable of perceiving a form of light utterly alien to our own experience. The breakthrough came not from building bigger and better optical telescopes, but from turning our attention to the radio spectrum. In the mid-20th century, the nascent field of radio astronomy began to listen to the sky, rather than just look at it. What they heard would forever shatter the illusion of the empty void. They were searching for a very specific cosmic whisper, a faint signal predicted by the Dutch astronomer Hendrik van der Hulst in 1944. He calculated that the most common atom in the universe, neutral hydrogen, should emit a faint but persistent radio wave at a precise wavelength 21 centimeters. This isn't a signal born of heat or light in the conventional sense. It is a quantum psi. Within each hydrogen atom, the single proton and single electron spin like tiny tops. On rare occasions, the electron will spontaneously flip its spin from aligning with the proton to opposing it, releasing a minuscule puff of energy in the process. This single photon, this 21 centimeter radio wave, is an impossibly rare event for any one atom occurring on average only once every 10 million years, but the interstellar medium contains an unimaginable number of hydrogen atoms. Across the vast plains of the galaxy, so many atoms are flipping their spin at any given moment that they collectively produce a faint, continuous hum. It is the background static of the Milky Way, the ambient sound of the cold, dark gas that fills the void. When radio telescopes finally tuned into this frequency in the early 1950s, the universe transformed. It was like switching from a black and white photograph to a thermal imaging map. Where our optical telescopes saw only disconnected points of light against a black background, the radio telescopes revealed immense swirling structures. Vast continent-sized clouds of neutral hydrogen gas, billions of times the mass of our Sun, were shown to be coiling through the spiral arms of our galaxy. These were the true cosmic reservoirs, the raw material from which future generations of stars would be born. We saw dense filaments connecting stellar nurseries and great bubbles of emptiness carved out by the explosive deaths of massive stars. The space between the stars was not a passive emptiness. It was a dynamic, turbulent and complex ecosystem. It was a place of currents and tides of weather patterns on a galactic scale, all utterly invisible to our eyes. We had discovered that our galaxy was not a collection of stellar islands in an empty ocean. It was a single, interconnected system where the empty space was the very lifeblood that sustained the stars. This revelation, as profound as it was, only addressed the emptiness within our own galaxy. An even greater void lay beyond the intergalactic space, the truly colossal abyss that separates one galaxy from another. If the interstellar medium was a near-perfect vacuum, then the intergalactic medium, or IGM, was a vacuum of an entirely different order. Here the density of matter was thought to drop by a factor of 1,000,000 perhaps, to as little as a single atom for every cubic metre of space. This was the ultimate desert, a realm of such profound emptiness that it seemed to defy the very concept of place. To detect a single atom per cubic metre across millions of light years seemed like a task beyond the reach of any conceivable technology. How could you possibly see something so close to nothing at all? The answer once again was to look not for the substance itself, but for the shadow it cast. And to cast a shadow across millions of light years you need an exceptionally powerful searchlight. Astronomers found their searchlights in the 1960s with the discovery of quasars. These are the hyperluminous cores of infant galaxies powered by supermassive black holes feeding on torrential inflows of matter. A single quasar can outshine its entire host galaxy by 1,000 times. They are the most brilliant beacons in the cosmos, and crucially they are located at the very edge of the observable universe. The light from a distant quasar has been travelling towards us for 10, 12, even 13 billion years. Its long journey is a direct path through the heart of that great intergalactic void. When we capture the light from a quasar and split it into its constituent colours, we get its spectrum, a chemical fingerprint of the object itself, and everything its light has passed through on its way to Earth. If intergalactic space were truly perfectly empty, the spectrum of a quasar would be smooth and continuous, marred only by the absorption lines from the quasar's own atmosphere. But that is not what we see. Instead, the spectrum is a chaotic, jagged mess. It is shredded by a dense thicket of thousands upon thousands of dark absorption lines. This astonishing feature is known as the Lyman Alpha Forest. Each and every one of those dark lines, each tree in that spectral forest, is the signature of a cloud of cold primordial hydrogen gas drifting in the vast emptiness between the galaxies. As the quasar's light sped across the cosmos, it intercepted these invisible ancient clouds. At each encounter, the hydrogen atoms in the cloud absorbed a very specific wavelength of ultraviolet light, the Lyman alpha line, before allowing the rest of the light to pass. Because the universe is expanding, each of these clouds is moving away from us at a different speed, causing the absorbed wavelength to be redshifted by a different amount. The result is not a single absorption line, but a forest of them, a complete historical record of the intergalactic gas the light has traversed. It was a forensic masterpiece etched into the oldest light in the universe. The void was not empty. It was filled with the wisps and tendrils of creation itself. We weren't seeing the gas directly, but we were seeing its undeniable effect. The nothingness had a tangible structure. With this new tool we began to map the unmappable. By observing the Lyman alpha forests of countless quasars in every direction of the sky, a breathtaking and unexpected picture began to emerge. The matter in the universe was not scattered randomly. The ISM within galaxies and the IGM between them were not separate entities. They were connected. They formed part of a single gargantuan structure that spans the entire observable cosmos, the cosmic web. On the larger scales, the universe resembles a three-dimensional spider's web or a celestial nervous system. Immense, sprawling filaments of tenuous gas, hundreds of millions of light-years long, stretch across the intergalactic voids. These filaments are the superhighways of the cosmos, funneling primordial hydrogen and helium across the universe. Where these filaments intersect, the density of matter grows, and it is here that gravity can finally win its long battle against cosmic expansion. These intersections are the nodes of the web, the cosmic cities, where clusters and superclusters of galaxies are born and thrive, and in between these glowing filaments, that is where we find the true void's vast, nearly empty bubbles, hundreds of millions of light-years across where the density of matter is even lower than in the filaments. These are the great deserts of the cosmos, but even they are not perfectly empty. They are simply the regions from which matter has been drained away, pulled by gravity, towards the glittering web that surrounds them. This is the grand architecture of reality, a universe built upon a ghostly scaffolding of cold, dark gas. Galaxies are not the main event. They are merely the bright condensed froth that has collected at the densest junctions of this invisible structure. Over 90% of all the normal baryonic matter in the universe does not reside inside stars or galaxies where we can easily see it. It resides out here in this cold, dark, and astonishingly beautiful web. The discovery of this web fundamentally changed our understanding of what a galaxy even is. It is not an isolated island universe sufficient unto itself. It is an open system constantly breathing in and breathing out. Galaxies are perpetually fed by cold streams of gas flowing in. Along the cosmic filaments, a process known as cold accretion. This inflow of fresh, pristine fuel is what sustains star formation over billions of years. Without it, a galaxy like our own Milky Way would have exhausted its gas reserves and stopped forming new stars long, long ago. And in return, powerful galactic winds driven by the combined energy of supernova explosions and active black holes blast enriched material back out of the galaxy and into the intergalactic medium. This is the universe's circulatory system. The intergalactic medium feeds the galaxies, and the galaxies enrich the intergalactic medium with the heavy elements forged in the hearts of their stars. So the void we once imagined as a static, sterile emptiness is in fact the most dynamic and crucial component of the entire cosmic ecosystem. It is the reservoir that holds the past and the promise that holds the future. It is the repository of the universe's primordial elements, and the recycling plant for materials created in the first generations of stars. Everywhere we had once seen nothing, we now saw the invisible engine of cosmic evolution at work. The cold, dark spaces were not an absence of creation. They were the very cradle from which creation continuously springs. We had answered the question of whether space was empty. The answer at every scale we could measure was a resounding no. But in doing so, we had uncovered a far more profound and tantalizing mystery. We had found the raw material, the immense clouds of frigid gas and dust that permeate the cosmos from the smallest interstellar clouds to the largest cosmic filaments. Now we had to ask the ultimate question of Genesis. How does this universe of cold, diffuse and nearly motionless matter ignite? How does this ghostly quiet give birth to the incandescent violence of a star? And yet something within this profound cosmic quiet refuses to be still. We've journeyed through the vast cold chasms between the galaxies, places where the lingering warmth of the Big Bang itself is the most dominant source of energy, a whisper of heat at just 3 degrees above absolute zero. It is a silence so complete, so ancient, it feels like the universe holding its breath. But this stillness is a grand illusion, an impossibly beautiful, deceptive piece. Because hidden within these frigid depths, the cosmos is not sleeping. It is dreaming. And from those dreams, it is building the future. To understand this breathtaking paradox, we must first travel 5,000 light-years from Earth toward the constellation Centaurus. Here we find a ghost, a celestial spectre so cold it defies our understanding of the universe. This is the Boomerang Nebula, and it is quite simply the coldest natural place we have ever discovered. While the background radiation of space keeps the universe at a balmy 3 Kelvin, the heart of this nebula has plunged to an astonishing 1 Kelvin. Just a single solitary degree above the theoretical point where all atomic motion would cease entirely. It is a cold that is not merely passive, it is aggressive, a place colder than the empty space surrounding it. How is this even possible? What could create a refrigerator in the middle of the cosmos, one capable of chilling itself below the faint residual glow of creation's first light? The answer lies not in stillness, but in extraordinary violence. At the centre of this ethereal bow-tie-shaped cloud is a dying star, an aging giant in its final convulsive throes. For the last 1,500 years this star has been hemorrhaging its own substance, blasting gas and dust outwards at a staggering velocity of over 500,000 kilometers per hour. This is not a gentle shedding of layers. It is a cataclysmic high-speed expulsion, a star tearing itself apart. And in this act of cosmic self-evisceration, we find the secret to its impossible cold. It is a principle you have felt yourself, even if you never realized its cosmic implications. When a pressurized gas expands rapidly, it cools down. It is the same phenomenon that makes a spray can feel cold as you use it. The gas molecules, once packed tightly together, are suddenly given room to spread out. They use their own internal heat energy to push outwards to do the work of expansion. And in spending that energy, they become colder. The dying star at the heart of the Boomerang Nebula has engineered this process on a scale that is almost unimaginable. It has created a celestial spray can 5,000 light-years away, venting its own atmosphere into the vacuum with such ferocious speed that the gas has undergone a profound adiabatic expansion, cooling itself to a temperature that should not exist in nature. So the coldest place in the universe is not some forgotten inert corner of the void. It is the direct ongoing result of a star's dramatic violent end. It is a place of extreme activity, of immense energy, transfer a testament to the fact that even in death, a star can rage against the quiet cold. The nebula itself is a preplanetary system, the raw material of future worlds frozen into a ghostly tableau. This object, this beautiful, chilling anomaly, serves as a profound signpost. It forces us to shatter our most basic intuition, the assumption that cold is synonymous with inaction, with emptiness, with the end of the story. Here in the coldest place we know we find a dynamic unfolding narrative, and this revelation is the key that unlocks one of the universe's greatest secrets. It invites us to look again at those other colossal reservoirs of cold we find scattered throughout our galaxy. Not the small ghosts of dying stars, but vast, sprawling continents of interstellar gas and dust. We call them giant molecular clouds, and they are the true heartlands of cosmic winter. Stretching for hundreds of light-years, containing the mass of 1,000,000 suns, these structures are magnificent dark tapestries woven against the stellar backdrop. To the naked eye they appear as stark absences of light, like the famous Horsehead Nebula, a dark silhouette against a crimson glow, or the coal sack, a patch of profound blackness in the river of the Milky Way. For centuries we thought they were simply holes in the fabric of the cosmos, windows into a deeper, more absolute void beyond. We were wrong. They are not holes, they are mountains, impossibly immense ranges of frigid hydrogen gas, helium, and complex dust so dense they completely block the light of the stars behind them. Inside these clouds, the temperature plummets often to a mere 10 to 20 degrees above absolute zero. They are shielded from the energetic radiation of nearby stars by their own dusty ramparts. Here atoms slow to a crawl. The universe is hushed dark and profoundly cold. By all accounts, these should be the most sterile, unchanging places in the galaxy. Cosmic graveyards where matter has come to rest forever, locked in a state of near absolute frost. And for a long time that is precisely what we believed. But the story of the Boomerang Nebula has taught us to be suspicious of stillness, to question the quiet. And as we peer deeper into the dark hearts of these molecular clouds, with instruments that can see beyond the visible spectrum detecting the faint radio waves, and infrared heat signatures trickling out from their cores, the illusion of peace is shattered once more. These cold, dark clouds are not tombs, they are wombs. They are the stellar nurseries of the galaxy. Against all logic, against all earthly intuition, it is here in the coldest, darkest, most seemingly desolate regions of space that new stars, new planets, and new hopes for life are born. This is perhaps the most glorious paradox in all of creation. That the incandescent fury of a star, a thermonuclear furnace millions of degrees hot, begins its life in a place defined by its proximity to absolute zero. How can this be? How does a cloud of diffuse near-motionless gas, a substance 1 billion times less dense than the air you're breathing, transform itself into a gravitationally bound, light-generating star? The answer is a battle fought on an epic timescale, a subtle patient war between two fundamental forces. On one side you have thermal pressure. Even in a cloud at 10 Kelvin, the individual atoms and molecules are still vibrating, still moving, still pushing against each other. This creates a faint outward pressure, a tendency for the cloud to remain diffuse, to expand. On the other side, there is the most patient and persistent force in the universe, gravity. Every single atom, every molecule, every grain of dust in that cloud pulls however feebly on every other. In a warmer, more energetic environment, the thermal pressure would win easily. The atoms would be moving too fast, pushing too hard for gravity's gentle whisper to be heard. But here in the deep abiding cold of the molecular cloud, the game changes. The cold is gravity's greatest ally. It saps the strength of thermal pressure, quieting the atoms, slowing them down until their outward push becomes weak, sluggish, vulnerable. The cold tilts the battlefield in gravity's favour, and so the process begins. It is not a dramatic implosion, but a creeping, inexorable surrender over millions of years. A region within the cloud, perhaps one that was slightly denser to begin with, by pure chance starts to contract under its own weight. Its gravitational pull, now infinitesimally stronger, begins to draw in more material from its surroundings. More gas, more dust. As it gathers more mass, its gravitational influence grows, and its ability to attract even more matter increases in a cosmic feedback loop. A gravitational runaway has been triggered. We call this collapsing core a protostar. Imagine yourself inside one of these nascent stellar systems, a privileged observer in the heart of creation. The darkness is absolute, a blackness deeper than anything on Earth. The cold is a physical presence, a palpable stillness. But you would feel something. A slow, steady drift. A sense of falling not downwards but inwards towards a centre that is not yet visible. Streams of hydrogen gas like ghostly rivers flow from all directions, converging on this unseen focal point. Over thousands of years, the density at the centre of this collapsing knot of gas climbs steadily. Molecules that were once light years apart are now crowded into a space the size of our solar system. And as they are crushed together, another fundamental law of physics ignites the process. Compression generates heat. The very act of gravitational collapse, the conversion of potential energy into kinetic energy, begins to warm the core of the protostar. The temperature begins to rise, from 10 Kelvin to 100, then 1,000, then 100,000. The cold that was so essential to begin the collapse is now being annihilated by it. A strange, dull, infrared glow would begin to permeate the darkness, the first blush of a new dawn visible only to specialized eyes. The cloud is no longer just a cold repository of gas. It is a cosmic embryo developing a warm beating heart. But the process is not smooth. The original cloud was not perfectly still. It possessed a subtle, almost immeasurable rotation, a legacy of the galaxy's own spin. As the cloud collapses, a principle known as the conservation of angular momentum demands that this rotation must speed up dramatically. It is the same reason a figure skater spins faster when she pulls her arms in. As the matter falls inward, it begins to whirl around the growing protostar, flattening into a vast spinning disk of gas and dust. A protoplanetary disk, the birthplace of worlds. Here, in this swirling, chaotic maelstrom surrounding the nascent star, a new chapter of creation begins. Within this disk, trillions upon trillions of tiny dust grains, many no larger than particles of smoke, begin to interact. These are not just inert specks of rock and carbon. In the intense cold of the outer disk, they are coated in layers of ice. Frozen water, methane, ammonia, carbon dioxide. They are sticky. As they orbit the central protostar, they collide. Sometimes they bounce off each other, but sometimes they stick together. An electrostatic charge, a fragile bond of ice, is all it takes. 2 grains become one. That one collides with another. The process repeats over and over, a patient cosmic game of accumulation. Grains become pebbles. Pebbles become rocks. Rocks smash together to form boulders, and boulders coalesce into planetesimals, the kilometre-wide seeds of future planets. It is a brutal, chaotic process, a demolition derby of creation. But out of this violence order emerges. A few planetesimals, through luck and gravitational advantage, grow faster than their neighbours, becoming the dominant gravitational bullies in their orbital zones. They sweep up the remaining debris, clearing their paths, growing over millions of years into the majestic spherical worlds we recognise as planets. All of this, the incandescent star, the swirling disk, the emerging planets, all of it was born from a silent, frigid, and impossibly vast cloud of molecular gas. Emptiness, it turns out, is the ultimate wellspring of substance. The cold is the crucible of fire. But the story grows even more profound. Because these cold clouds are not just building stars and barren rocks, they are also cosmic laboratories engaged in the most delicate and complex chemistry. The very dust grains that serve as the building blocks of planets also act as microscopic meeting places, catalytic surfaces for atoms to find each other. An isolated hydrogen atom drifting through the cold dark might wander for 1,000 years before encountering another atom. But when it strikes the frozen surface of a dust grain, it can get stuck, held in place by the grain's icy mantle. Soon, another hydrogen atom might arrive, and another. Shielded from destructive starlight and held in close proximity on this frozen scaffolding, these atoms can finally bond, forming molecular hydrogen, the primary fuel for the new star. But it is not just hydrogen. Carbon, oxygen, nitrogen. The fundamental elements of life are all present in these clouds. On the surfaces of these unimaginably cold dust grains, a rich and complex organic chemistry begins to unfold. Ultraviolet light from distant stars trickling through the cloud provides just enough energy to break and reform chemical bonds. Simple molecules like water and methane are forged into more complex structures. Formaldehyde, methanol. Even amino acids, the very building blocks of proteins, have been detected in the spectra of these stellar nurseries. Think of what this means. Long before the star at the centre of the disk has even ignited nuclear fusion, long before the planets have fully formed, the raw prebiotic ingredients for life are being manufactured in abundance. They are being cooked in a cosmic kitchen where the oven is near absolute zero. These life-giving molecules are then incorporated into the very comets, asteroids and planetesimals that will eventually build the new worlds. The process seeds the planets with the potential for life from the moment of their birth. Every star you see in the night sky was born this way. Our own sun, our Earth, everything we are and everything we know is a direct product of one such cold, dark molecular cloud that collapsed 4.5 billion years ago. We are the descendants of cosmic winter. The matter in your body, the carbon in your cells, the oxygen you breathe once drifted through a silent, frigid darkness, waiting for the patient, relentless call of gravity to gather it together and begin the epic journey towards light, warmth and consciousness. The realization that these cold regions are not voids, but engines of creation represents one of the most significant shifts in our perception of the universe. It turns our entire cosmology on its head. The story of the cosmos is not just a story of cooling down from a hot, fiery beginning. It is a cyclical, regenerative story where the cold itself becomes the essential catalyst for the next generation of fire and light. These clouds are the galaxy's memory holding the enriched material from long-dead stars, and they are the galaxy's future providing the raw substance for stars yet to be born. But this birth process is not gentle. The transition from a quiet, collapsing core to a fully fledged shining star is one of the most violent and spectacular events in the cosmos, an act of celestial trauma that will shape the entire planetary system for billions of years to come. The newborn star must fight its way out of the very cocoon that nurtured it, and in that fight it will unleash forces that are both creative and profoundly destructive. And so this portrait of the cosmos, painted with the faint light of 1 trillion galaxies adrift in the cold, is fundamentally incomplete. The arithmetic simply does not work. When we measure the great cosmic voids, when we watch the galaxies that skate along their precipitous edges, we encounter a profound violation, a law of physics seemingly broken on the grandest scale imaginable. These island universes are moving with an impossible velocity. They orbit the centres of their clusters far too quickly, whirling with a speed that should by all accounts fling them outwards into the intergalactic darkness forever. The gravity generated by all the stars, all the gas, all the dust we can see, every luminous speck accounted for, is woefully insufficient. It is like watching a child on a merry-go-round spinning at the speed of a jet turbine. The chains holding the seats should have snapped, hurling them into the distance. Yet they hold. Something else is there. An invisible hand, a gravitational anchor of immense power, is binding these galaxies together, preventing their dissolution. This discrepancy, this maddening gravitational ghost, was not a discovery made in the age of supercomputers and space telescopes. It was first glimpsed nearly a century ago through the stubborn eyes of a brilliant and irascible astronomer named Fritz Zwicky. While studying the Coma Cluster in the 1930s, he saw this same impossible speed, this same cosmic incongruity. He calculated the mass of the visible stars and found it was off not by a small margin, but by a staggering factor of over 400. Zwicky postulated the existence of what he called dunkel Materie, dark matter. His idea was largely dismissed, a phantom born of faulty observation perhaps. For decades it remained a fringe concept, a footnote in the cosmic story. The universe, it was assumed, was made of the same stuff we are. Protons, neutrons, electrons. The familiar tangible elements of the periodic table. But the ghost would not rest. It reappeared in the 1970s in the meticulous work of Vera Rubin. She wasn't looking at distant clusters, but at the stately rotation of individual spiral galaxies, much like our own Milky Way. Physics predicted a simple outcome: stars farther from the galactic centre, where the visible mass is concentrated, should move more slowly, just as Neptune plods along in its orbit compared to the swift Mercury. Instead, Rubin found something that defied all logic. The stars on the outermost fringes of the galaxies were moving just as fast as the stars near the core. The rotation curves were flat. It was a stunning, universe-altering discovery. The only way to explain this was if every single galaxy was embedded in a vast spherical halo of unseen matter, a colossal sphere of gravitational influence extending far beyond the visible light. Zwicky's ghost was not just real. It was everywhere. This is not dark in the sense of being black or shadowy. It is dark in the sense of being utterly, perfectly transparent. It does not emit light. It does not reflect light. It does not absorb or block light. Light, and indeed all forms of electromagnetic radiation, passes through it as if it weren't there at all. It is an entirely separate form of substance, a cosmic phantom, that has only one known way of interacting with our universe: through gravity. This realization forces us to redraw our map of existence. The brilliant filaments of the cosmic web, the glowing superclusters, these are not the primary structure of the universe. They are merely the decorations. The true architecture, the unseen scaffolding upon which everything is built, is a vast and intricate network of dark matter. Imagine a titanic invisible skeleton spanning the cosmos. The galaxies we see are like tiny glowing nerve cells that have coalesced along the densest points of this skeleton. They trace its form, illuminating its presence, but they are a trivial fraction of its total mass. And the great voids, they are the cavernous spaces between the bones. They are empty of luminous matter precisely because the immense gravitational pull of the dark matter filaments has spent 13 billion years systematically shepherding normal matter out of them. Like cosmic rivers, the gravity of these filaments has guided the primordial hydrogen and helium, pulling it away from the voids and into these dense channels where it could eventually collapse to form the stars and galaxies we see today. The voids are a direct and necessary consequence of this unseen universe of dark matter. They are the clearest proof of its architectural power. We can even see its effects directly written in the fabric of space-time. Einstein taught us that mass warps space, and that light follows these warps. This effect, called gravitational lensing, turns massive objects into cosmic telescopes. When we point our instruments to the sky, we can see the light from incredibly distant galaxies, and quasars being bent, distorted and magnified as it passes by a closer galaxy cluster. The trick is to measure just how much the light is being bent. From that distortion, we can calculate the mass of the object doing the lensing, and time again the result is the same. The mass required to create the observed lensing effect is 5 to 6 times greater than the mass of all the visible matter combined. We are literally seeing the gravitational footprint of something we cannot see. The light from the farthest reaches of the universe is being warped as it travels through the voids bent by the invisible filaments of dark matter that form their boundaries. We are watching light bend around nothing. The most compelling evidence, however, comes from the universe's baby picture. The cosmic microwave background radiation. The afterglow of the Big Bang is not perfectly uniform. It is mottled with tiny temperature fluctuations, infinitesimal variations in density in the primordial soup. These minuscule seeds, just 1 part in 100,000, are the origin of all cosmic structure. Gravity acting over billions of years amplified these tiny dense spots, pulling in more and more matter until they grew into the galaxies and clusters we see today. But there is a problem, a fatal one for a universe made only of normal matter. In the fiery, dense early universe, the outward pressure of light and radiation was immense. For every particle of normal matter that tried to clump together under gravity, the intense radiation would have blasted it apart. Structure simply could not have begun to form until the universe had expanded and cooled enough for atoms to form hundreds of thousands of years after the Big Bang. And that is not enough time. 13 billion years is simply not long enough for gravity starting from such a late stage to build the colossal structures we witness. Our simulations are unequivocal. A universe with only normal matter would today be a thin, largely uniform fog, not this rich cosmic tapestry. Unless there was another substance present from the very beginning. A substance that did not interact with light. A substance immune to that ferocious outward pressure. Dark matter. It provided the silent gravitational wells. While normal matter was being buffeted by radiation, the dark matter impervious began to quietly clump together in the primordial dark, amplifying those initial density seeds. It dug the gravitational trenches. When the universe finally cooled and the radiation pressure subsided, the normal matter, now free to move, simply fell into the deep gravitational wells that the dark matter had already prepared. Without this invisible gravitational shepherd, you would not be here. Our galaxy would not be here. The universe as we know it could not exist. The voids would not be voids, and the filaments would not be filaments. It is the silent, invisible majority 5 times more abundant than all the atoms in the cosmos combined. And yet this is only half of the story. Solving one profound mystery has only led us to another one that is deeper, stranger, and far more consequential for the universe's ultimate fate. For as we refined our cosmic maps, as we peered deeper into the voids and measured the expansion of the universe with unprecedented precision, we found something that should not be happening. The expansion is not slowing down. Gravity, the attractive force of all this matter, both normal and dark, should be acting as a cosmic brake, gradually slowing the stretching of space-time that began with the Big Bang. For most of the 20th century, the central question in cosmology was whether the universe had enough mass to eventually halt its expansion and collapse back in on itself in a big crunch, or not enough, allowing it to expand forever, but at an ever-decreasing rate. No one was prepared for the third option. In the late 1960s, 2 independent teams of astronomers set out to measure this deceleration. They used a specific type of stellar explosion, a type Ia supernova, as a standard candle. These supernovae always explode with the same intrinsic brightness, meaning we can use their apparent dimness to calculate their distance with incredible accuracy, and by measuring their redshift we can determine how fast they are moving away from us. This allows us to look back in time and plot the history of cosmic expansion. The teams pointed their telescopes towards the distant past, expecting to find that supernovae long ago were receding faster than the deceleration of the universe would predict. They found the exact opposite. The distant supernovae were dimmer and therefore farther away than they should have been. The universe in the past was expanding more slowly than it is today. The expansion of the universe is not slowing down. It is accelerating. It was a result so staggering, so contrary to all expectations, that the team spent months checking their data, searching for any possible error. But the conclusion was inescapable. Some unknown force, some mysterious repulsive energy is embedded in the fabric of space itself, and it is pushing the universe apart. We call it dark energy. Unlike dark matter, which clumps together gravitationally and forms the structure of the cosmic web, dark energy appears to be smooth, uniform, and ubiquitous. It seems to be a property of the vacuum and intrinsic energy of space itself, and it has a bizarre, almost insidious quality. The more space there is, the more of this energy there is. As the universe expands, it is literally creating more of the very stuff that drives the expansion faster. It is a runaway feedback loop on a cosmic scale, and it is in the vast, cold voids where this mysterious force truly rules. In the dense filaments and clusters of the cosmic web, gravity is still king. The immense concentration of dark matter and normal matter creates a gravitational field strong enough to overcome the repulsive push of dark energy. Galaxies within a cluster are not flying away from each other. They are bound together. The Andromeda Galaxy is not accelerating away from us. It is on a collision course with our Milky Way. But out in the desolate emptiness of the voids there is almost nothing. No significant concentrations of galaxies, very little dark matter. Gravity here is weak, almost non-existent. And in this vacuum, dark energy is unopposed. The voids are not just passive empty regions. They are the engines of cosmic acceleration. Each cubic meter of the void is imbued with this ethereal pressure, pushing outwards on the surrounding walls of the cosmic web. The voids are actively, powerfully growing, stretching the filaments thin, and pushing the galaxy superclusters farther and farther apart from one another. This is the ultimate cold. Not just the cold of empty space, but a cold born of an accelerating expansion that isolates everything. The emptiness is not empty at all. It is filled with a phantom ocean of repulsive energy, the most dominant component in the entire universe. So now we must face the modern cosmological census, a portrait of reality that is both breathtakingly humbling and deeply unsettling. Everything we have ever known, every star, every planet, every atom, all the stuff of our existence constitutes a mere 5% of the universe. 27% is the invisible gravitational scaffolding of dark matter, the silent architect of the cosmos. And the remaining 68%, the overwhelming majority, is this enigmatic dark energy, a repulsive force woven into space-time, driving the universe towards a cold, isolated and accelerating future. Our universe is not defined by the brilliant light of its stars, but by the profound darkness that lies between them. It is a cosmos governed by two invisible phantoms whose true nature remains one of the greatest unsolved mysteries in all of science. We see their influence everywhere. We see it in the impossible spin of a galaxy and in the ever-widening gulf of a cosmic void. We have mapped their shadows, measured their effects, and calculated their abundance. And yet we stand on the precipice of a vast intellectual chasm, staring into an abyss of ignorance. What is the dark matter particle? Is it a theoretical heavy particle, a WIMP that only interacts through the weak nuclear force, or is it something far more exotic and axion, a sterile neutrino, or a remnant from an even earlier, stranger phase of the universe? And what fundamentally is dark energy? Is it Einstein's cosmological constant, a simple unchanging energy of the vacuum, or is it something dynamic, a field that changes over time, a quintessence whose future behavior we cannot yet predict? These are the questions that now drive us. They compel us to build detectors in the deepest mines on Earth, hoping to catch the whisper-faint signal of a dark matter particle passing through our planet. They push us to launch new telescopes into space designed to map the geometry of the cosmos with ever greater precision, searching for the faintest clues about the nature of the dark energy that defines our destiny. The coldest, emptiest places in the universe are not a final destination. They are a new beginning. They are the laboratory where the fundamental nature of reality is being laid bare, and the hunt for the truth has only just begun. We have discovered a dark universe, and now we must learn to see within it. And so we have finally arrived. Through a journey across the cosmic dark past the final whisper of the background radiation, we have imagined a perfect vessel, a theoretical box of reality shielded from every photon, every stray atom, every last vestige of the material universe. We have cooled it in our minds to the impossible stillness of absolute zero, a temperature where all classical motion is meant to cease. We have engineered the ultimate void, the final pristine state of nothingness. This is the endpoint of entropy, the quietest, coldest, darkest place imaginable. Here at last, in this perfect vacuum, the story of the universe not being empty should finally find its conclusion. The restless dance of matter and energy should be over, but it is not. Here at the very floor of existence, where all the familiar rules of our world have been stripped away, we find that the universe has one last stunning secret. We discover that even when you have removed everything, there is still something left. A profound and unsettling truth is revealed not by classical physics, the physics of planets and stars, but by its strange and far more fundamental successor. To understand what remains in our perfect void, we must leave behind the comfortable world of cause and effect, and descend into a realm of pure potential, a world governed by the bewildering laws of quantum mechanics. This is a universe where particles can be waves, where an object's position and momentum can never be known at the same time, and where reality itself seems to shimmer with an inherent irreducible uncertainty. It was this very uncertainty first codified by the German physicist Werner Heisenberg that provided the first clue that a true void might be a physical impossibility. Heisenberg's uncertainty principle is not a statement about the limits of our measuring devices. It is a fundamental law of nature. It proclaims that there is a cosmic trade-off, a non-negotiable bargain between certain pairs of properties, like energy and time. You can know the energy of a system with perfect precision, but only if you observe it for an infinite amount of time. Conversely, if you look at a system for an infinitesimally brief moment, its energy becomes almost infinitely uncertain. This principle is the master key. It applies not only to the particles we can see and touch, but to the underlying fields from which they arise. Quantum field theory tells us that the universe is permeated by invisible fields, one for each fundamental particle. There is an electron field, a photon field, a quark field, and so on. These fields are the true bedrock of existence. What we perceive as particles are merely localized energetic vibrations in these fields, like a flicked string on a cosmic guitar. When you remove all the particles from our theoretical box, you're not left with a true nothing. You're left with the fields themselves in their lowest possible energy state, their ground state. You're left with the silent, dormant potential for everything. And according to Heisenberg, for even the briefest instant, that ground state cannot have a perfectly defined energy of zero. The cosmic law of uncertainty forbids it. Over incredibly short timescales, the energy in any given point of our vacuum must fluctuate. It must roil and tremble with a borrowed phantom energy. Space itself, in its most empty state, is possessed of a fundamental restlessness. It is a lender operating on the most extreme timescales imaginable, offering fleeting loans of existence from the bank of pure potentiality. And with these loans of energy, something spectacular happens. Out of absolutely nothing for a sliver of time so short it defies human comprehension, a pair of particles erupts into being. A particle and its corresponding antiparticle, an electron and a positron, a quark and an antiquark blossom from the void, brought into existence by this momentary loan of energy. They live an impossibly brief life, a frantic ephemeral dance in the darkness before they find each other once more, and annihilate, repaying the energy loan to the vacuum and vanishing as if they had never been. These are not the solid, stable particles that form you and me. They are virtual particles, ghosts in the machine of reality. They are the universe's secret, a constant flickering heartbeat beating in the heart of the void. Imagine an ocean perfectly calm and glassy on its surface. This is the classical vacuum, the serene emptiness we expected to find. But the quantum view shows us that deep beneath the surface, the water is a chaotic maelstrom of currents, eddies, and whirlpools constantly in motion. This is the quantum vacuum. At every point in space, at every single moment, this seething ocean of virtual particles is churning. Billions upon billions of them, a phantom foam of existence, are born and die in a femtosecond. They are the fleeting expressions of all the matter and energy that could be a constant reminder that the fabric of space-time is not a passive backdrop to the cosmos. It is a dynamic, energetic medium, alive with potential. Our perfect void, the coldest, darkest place in the universe, is in fact the most crowded. It is a roiling, effervescent soup of possibilities, a ghostly particle blizzard raging in the heart of nothingness. This idea might seem like a fever dream of theoretical physics, a mathematical fantasy with no connection to the real world. For decades it remained just that. How could you ever prove the existence of something that lasts for less than a trillionth of a second? You cannot see them, you cannot capture them. They are by their very definition virtual, but their effects, it turns out, are not. The ghostly ocean of the quantum vacuum can exert a very real, very measurable force. The proof came in 1948 from the Dutch physicist Hendrik Casimir. He imagined a scenario that was at first glance achingly simple. Take two perfectly flat, uncharged metal plates. Place them parallel to each other in a perfect vacuum, just a few micrometers apart. According to classical physics, absolutely nothing should happen. The plates are uncharged, so there is no electromagnetic attraction or repulsion. There are no air molecules between them to exert pressure. In the cold, empty void, they should remain perfectly motionless, suspended in eternal stillness. But Casimir realized that the quantum vacuum would see this situation very differently. He understood that these virtual particles are not just particles, they are also waves. Specifically, they are quantum fluctuations of the electromagnetic field, virtual photons of every conceivable wavelength flickering in and out of existence. Outside the plates in the vast expanse of the surrounding vacuum, virtual photons of all wavelengths can exist. There are no restrictions. The ghostly sea can churn with waves long and short, but between the plates, things are different. The tiny gap acts as a resonant cavity. Only virtual photons whose wavelengths fit a whole number of times into the gap can exist there. Longer wavelengths are excluded. They simply don't fit. This means there are fewer possible modes of fluctuation, fewer virtual particles popping into existence in the space between the plates compared to the space outside the plates. The result is a subtle but profound imbalance. The seething ocean of virtual particles on the outside of the plates is more energetic, more crowded than the comparatively calmer sea on the inside. This creates a pressure differential. The vacuum outside pushes on the plates more than the vacuum inside. A force manifests out of pure nothingness, a force generated by the fleeting ghosts of reality pushing the two plates together. This is the Casimir effect. It is the vacuum itself flexing its muscles. It is the sound of one hand clapping played out on a cosmic scale. When the experiment was finally performed with sufficient precision decades later, the results were undeniable. The plates moved. A measurable force born from the quantum foam had pushed on our tangible macroscopic world. Suddenly, the vacuum was no longer a passive void. It was an active participant. Its ghostly inhabitants, once relegated to the realm of pure theory, were now known to be real, their collective presence capable of shifting objects in our own world. This discovery transformed our understanding of emptiness forever. Space is not a stage upon which the cosmic drama unfolds. It is an actor in that drama, and this actor possesses a truly astonishing amount of energy. When physicists tried to calculate the total energy density locked away in the quantum fluctuations of the vacuum, they arrived at a number that was stupefying. It was, to put it mildly, the worst prediction in the history of physics. The theoretical energy density of the vacuum, the sheer power simmering in every cubic centimetre of empty space, was calculated to be about 120 orders of magnitude. That is a 1 followed by 120 zeros, greater than anything we observe in the universe. If this calculation were correct, the energy inherent in a space the size of a light bulb would be enough to boil every ocean on every planet in the entire known cosmos instantly. The gravitational effect of this energy would be so immense that it would have curled the universe up into a tiny ball smaller than an atom just moments after the Big Bang. Our universe should not exist. It should have collapsed before it even began, crushed by the astonishing weight of its own emptiness. And yet here we are. We live in a large, expanding and relatively stable universe. This colossal discrepancy, this chasm between the theoretical energy of the void and the observed reality of our cosmos, is known as the cosmological constant problem. It is arguably the single greatest and most profound mystery facing modern physics. It tells us that we are missing something fundamental in our understanding of how the universe works, some unknown principle of nature that is cancelling out almost all of this titanic vacuum energy, leaving behind just the tiniest, most delicate residue. And that residue is where the story takes its most dramatic turn. Because while the vacuum's energy is not nearly as large as our theories predict, it seems it is not exactly zero either. For the past 2 decades, astronomers have been watching the distant galaxies and have come to a shocking conclusion. The expansion of the universe is not slowing down under the pull of gravity as everyone had expected. It is accelerating. Some mysterious anti-gravitational force is pushing space-time apart, driving the galaxies away from each other at an ever-increasing speed. They have given this mysterious influence a name: dark energy. Dark energy comprises nearly 70% of the total energy density of the cosmos. It is the dominant force in the universe shaping its ultimate destiny, and we have absolutely no idea what it is. But the leading candidate, the one that haunts the dreams of cosmologists, is that dark energy is nothing less than the faint residual energy of the vacuum itself. It is the ghost in the machine now writ large across the entire cosmos. The same quantum foam that pushes 2 tiny plates together in a laboratory may be the very same force that is pushing the entire universe apart. The restless energy of the void, born from the fundamental uncertainty of existence, has become the architect of our cosmic future. We began this journey by seeking the coldest, most desolate corner of reality, a place defined by its profound absence. Instead, we have found the opposite. We have discovered that the fundamental state of the universe is not a tranquil nothingness, but a ceaseless, violent, and unimaginably energetic storm of potential. The state of non-being is inherently unstable. The universe, it seems, abhors a true vacuum, and from its quantum heart it insists on filling every crevice with a ghostly hum of creation and annihilation. Emptiness is an illusion. The coldest place in the universe is a furnace of virtual reality, a place where the laws of physics themselves prevent stillness and silence from ever truly taking hold. This quantum realm, this bedrock of existence, proves that even in the most profound isolation, there is an eternal dynamic connection to the whole. The energy that defines the ultimate fate of the largest cosmic structures may be born from the impossibly small fluctuations occurring in every microscopic point in space, including the space in the room around you right now, and the space within the atoms that make you. We are all quite literally swimming in an ocean of this phantom energy. The implications are staggering, forcing us to reconsider the very nature of reality and our place within it. If the vacuum itself is this powerful, this fundamental, could it hold the key not just to the universe's expansion, but to its very origin? What happens when you take this seething, energetic quantum foam and apply it to the single, infinitely dense point that existed before the Big Bang? Could the universe itself be nothing more than a grand fluctuation, a virtual particle on a cosmic scale borrowed from an even greater nothingness? The void, it turns out, is not the end of the story. It may very well be the beginning. And so we arrive at the end of a journey that began with a simple, intuitive, and profoundly human assumption that cold is an absence, that to be cold is to be without energy, without light, without life. We have travelled from the shimmering heat of our own star to the absolute edge of temperature chasing a ghost we call zero, only to find that our assumption was not just wrong, but magnificently, beautifully, and fundamentally incorrect. What we once perceived as the void is not a void at all. It is a stage. It is the silent, sprawling theatre where the universe's deepest and most enduring dramas unfold, hidden from the blinding glare of its own incandescent stars. We began our descent in the phantom breath of the Boomerang Nebula, that spectral cloud expanding into the blackness, chilling itself to a single degree above the ultimate cold. There we witnessed thermodynamics in its most extreme and elegant form, the universe itself acting as a colossal refrigerator, demonstrating that even the act of rushing into emptiness creates a profound physical state. It was not nothingness we found, but a testament to the laws of motion and energy, a cosmic monument to the universe's own relentless expansion, etching its signature in a frost of impossible cold. That chilling whisper was our first clue, the first hint that the dark, silent corners of the cosmos were not empty pages, but were in fact densely written texts in a language we were only just beginning to decipher. From that isolated outpost of extreme cold, Our perspective widened, pulling back to reveal the grand skeletal structure of the cosmos. We soared through the vast intergalactic voids, those immense bubbles of seeming emptiness that separate the glittering chains of galaxies. For generations we saw them as cosmic deserts, barren expanses to be crossed as quickly as possible on our intellectual journey from one island of light to another. Yet with our new eyes, with instruments tuned to the faintest frequencies and the most subtle gravitational whispers, we have found that these voids are not empty. They are permeated by the thinnest, most ancient hydrogen gas leftovers from the Big Bang, a ghostly web connecting everything to everything else. More profoundly, these cold voids are the undisputed kingdom of the universe's two greatest mysteries, dark matter and dark energy. Here in the profound cold and dark, where the gravitational influence of stars and galaxies finally fades, the true ruler of the cosmos makes its presence known. The gentle, persistent, anti-gravitational push of dark energy dominates, accelerating the expansion of space itself, pushing the galaxies apart with an inexorable force we can measure but cannot yet explain. And laced through it all is the invisible scaffolding of dark matter, the gravitational bedrock upon which the entire visible universe is built. These cold, dark places are not where the universe ends. They are where its fundamental operating system runs silently and efficiently in the background. The universe is not empty. It is simply haunted by the gravitational ghosts of matter we cannot see and driven by a strange energy woven into the fabric of space-time itself. Our journey then took us from the impossibly large to the intimately creative, diving deep into the frigid hearts of molecular clouds, the stellar nurseries scattered throughout our own galaxy. We ventured into places like the Pillars of Creation and the Orion Nebula, places that appear to our eyes as dark, obscuring smudges against a backdrop of stars. Here, temperatures plunge to just 10 or 20 degrees above absolute zero. It is a cold so intense that atoms cling together, forming the simple molecules that are the raw ingredients for life and worlds. And it is in this precise, profound chill that the universe's most spectacular act of creation begins. Here, the relentless, chaotic push of thermal energy finally subsides, quieting the cosmic storm. In the stillness, a more patient, more fundamental force can finally assert its authority: gravity. We watch the slow, delicate dance of gas and dust, a cosmic ballet choreographed over millions of years. We saw gravity gently coaxing these frigid materials into denser and denser clumps, pulling them together into spinning protostars. The cold, you see, is not the enemy of creation. It is its essential incubator. It is the quiet moment of cosmic inhalation before the fiery exhalation of a new star. Without these intensely cold, dark pockets of space, gravity would never win the fight against pressure. The universe would be a uniform, lukewarm, and utterly sterile soup. Every star you have ever seen, every planet that has ever formed, including our own, owes its existence to a place that was once profoundly, creatively, and necessarily cold. This revelation forces us to reconsider the very nature of potential. We look at a star and see power, energy, and light. We are naturally drawn to it, but the universe in its subtle wisdom stores its greatest potential in the opposite condition. A cold molecular cloud holds within it the promise of 1,000 future suns, 1,000,000 future worlds. It is a promise written in the language of quantum mechanics, of molecules vibrating in the near absolute silence. It is a testament to the fact that the universe's story is not just one of explosive endings of supernovas and gamma ray bursts, but also of these slow, quiet, and intensely cold beginnings. The silence of the cold is the sound of the future being built. And then we turned our senses to the entire sky, to the faintest and most ancient signal in all of creation, the cosmic microwave background, the afterglow of the Big Bang itself, at a uniform 2. 7 to Kelvin, it is the baseline temperature of the universe, the coldest thing there is on a grand scale. It is the universe's final fading whisper from its own violent birth. For decades we saw it as a nearly perfect uniform curtain of light, a baby picture of the cosmos in its infancy. But as our instruments grew more sensitive, we began to see the imperfections. We discovered the most subtle variations, tiny fluctuations in temperature differences, of mere millionths of a degree. These are the most important imperfections in the history of the universe. These are not flaws, they are seeds. The slightly colder, denser spots in that primordial fire were the kernels of gravitational collapse. They were the initial blueprints from which everything else would eventually grow. Over billions of years, these minuscule cold spots attracted more and more matter, growing into the first stars, the first galaxies, and eventually the colossal superclusters that decorate our universe today. When you look at the map of the cosmic microwave background, you are not looking at an artifact. You are looking at a prophecy. You're seeing the promise of every structure in the modern cosmos foretold in a language of temperature, written across the entire sky when the universe was less than 400,000 years old. Our entire complex structured universe with all its warmth and life is the direct descendant of those faint cold patches in the afterglow of creation. The cold, once again, was not an absence, it was the presence of a plan. So what does this all mean for us? It means we must fundamentally overhaul our cosmic perspective. The illusion of a barren cosmos has been shattered not by finding life on other planets, but by redefining what it means for the universe itself to be alive. We are accustomed to looking for life in warm, wet places like our own Earth, tiny oases in a vast cold desert. But this journey has taught us that the desert itself is teeming with a different kind of life, a life of physical law, of creative potential, of unseen influence and slow, majestic change. The universe is full. It is full of quantum fields fluctuating even in the most perfect vacuum. It is full of gravitational waves rippling silently through the coldest voids. It is full of the overwhelming presence of dark matter, shaping galaxies from the outside in. It is full of the accelerating power of dark energy determining the ultimate fate of everything. And it is full of the raw, cold potential for new stars and new worlds sleeping in the dark. The universe is not a collection of objects separated by nothing. It is a single interconnected entity, a dynamic and vibrant arena where the most profound forces are those that operate in the dark and the cold. We have learned that our senses evolved to navigate a sun-drenched planetary surface are profoundly biased. We are creatures of warmth and light, and so we have projected our own needs onto the cosmos, believing that warmth and light are the only things that matter. But the universe is not obligated to conform to our biology. Its story is far grander, far stranger, and far more complete. To truly understand it, we had to learn to see with new senses with radio telescopes that can hear the whispers of cold hydrogen, with infrared cameras that can pierce the dark dust of stellar nurseries, with gravitational detectors that can feel the tremors of space-time itself. With these new senses, we have peeled back the curtain of visible light and stared into the universe's hidden heart. And what we have found there is a place of sublime and elegant physics, a place where the rules of reality are laid bare. We have discovered that the coldest places in the universe are in fact the most informative. They are the quiet libraries where the universe's oldest secrets are kept waiting for a patient reader, and our reading has just begun. The next generation of observatories, our future eyes and ears on the cosmos, are being designed specifically to probe these frigid frontiers with even greater precision. The James Webb Space Telescope and its successors are tuned to the infrared light that shines from the first galaxy's light that has been travelling through the expanding, cooling universe for over 13 billion years. They will peer back through cosmic dawn to witness the moment when the first stars condensed out of the cold, primordial darkness, setting the universe ablaze for the first time. They will stare into the hearts of stellar nurseries with such clarity that we may be able to see planetary systems in the very act of coalescing from frigid disks of gas and dust. Meanwhile, new radio arrays, vast networks of telescopes spread across entire continents, will map the faint radio hum of neutral hydrogen from the universe's dark ages, the era before the first stars ignited. They will provide the first three-dimensional maps of this cold, transparent epoch, allowing us to watch for the first time as those initial cold spots in the cosmic microwave background begin to pull matter together to see the first gravitational scaffolding of the cosmic web taking shape. And our quest to understand the unseen will become even more ambitious. Experiments buried deep underground, shielded from the noise of our own world, we'll continue to listen for the whisper-faint interaction of a dark matter particle, a ghost, from the cold cosmos passing through the Earth. New space missions will map the geometry of the universe with unprecedented accuracy, seeking to understand the nature of the dark energy that thrives in the cold voids. Each of these endeavours is a journey deeper into the cold, a recognition that the next great revolutions in our understanding of the universe will not come from looking at the brightest objects, but from deciphering the faintest signals emanating from the darkest, coldest corners of reality. We stand now at a precipice of understanding. We have looked into the abyss and found it staring back not with an empty gaze, but with the intricate, complex and beautiful fullness of a living system. We have learned that the absence of heat is not the absence of story. Instead, it is the quiet canvas upon which that story is painted. The universe is a masterpiece composed in equal parts of light and shadow, of fire and ice, of sound, and of a silence so profound it contains the echo of creation and the promise of all that is yet to be. Your journey, our journey, began with a glance at the night sky, at the pinpricks of light scattered across a seemingly empty blackness. But you will never see that blackness in the same way again. You know now that it is not an absence, it is a presence. It is the womb of stars, the realm of invisible forces, the repository of cosmic history. It is the place where the universe dreams, and as we continue to build our tools and sharpen our minds, we will continue to listen to those dreams, drawing ever closer to the ultimate truth of our cosmos, that even in its deepest, most absolute cold, the universe is, and has always been, incandescently alive.